Bam! Mr. Tarot. In this math lesson, we are going to be talking about the inverse of power functions. That is an equation that's in the form of y equals a times x to the b power. It's a sort of like a one-term polynomial. And we're going to be discussing the algebraic steps it takes to write the inverse of a given function. We're going to be talking about graphical representation. How is the graph of a function and its inverse related to each other? We're going to be then, graphing an inverse with this particular example here. And this is going to open up the door to let you see that an inverse is not always a function. Even if you start with a function, the inverse may or may not be a function. So we'll be determining if we can find an inverse function from a given function. Or in other words, is this a one-to-one function or is it an invertible function? Do a couple of examples based off of that. And then finally finish off with kind of an example similar to this where we're given a function and we're asked to graph the inverse function. It'll be a more complicated example than we have here with just simply y equals x squared. Now the algebraic steps. If I give you a function and I say find its inverse, you're just simply going to rewrite the equation and swap the independent and dependent variables. So this will be written as basically x equals a times y to the b power. And then you resolve for y. So the roles of the independent and dependent variable, not always, but often labeled as x and y, they change. They change role. The function is sort of working in reverse. Like in trig, this concept is going to come back over and over and over again. And when you're taking trig, when you take the sine of an angle, you get the sides of a reference triangle. I know you're probably not in trig yet, but when you talk about an inverse trig function, you're putting in the sides of the reference triangle and getting out the amount of rotation or the angle measure. So that's what's going on here. The roles of the independent and dependent variables are changing. The equation is effectively working in reverse, if you will. Now, through this lesson and the ones coming up, you're going to be seeing this little notation, which is an exponent of -1. In function notation, that means you're looking at an inverse, but you don't want to use that notation unless the inverse is actually a function as well. Remember, we'll be talking about determining whether a function will have an inverse function, not just an inverse. Now, I kind of want to pause here and give you a little side note that when you see just negative exponents in a numerical fashion, that means if you want to rewrite this so that you don't have a negative exponent, you're going to move the base that has that negative exponent. So 5 to the -1 is equal to 1/5 to the 1 power. And in an upcoming lesson here soon, I'll explain exactly how moving the base, either from the numerator to the denominator or from the denominator to the numerator, allows the sign of that exponent to change. So you might be thinking that negative exponents simply mean to flip the base or write a reciprocal. That, again, you can see with how to create an inverse where the roles of the independent and dependent variables change. That notation does not mean the same when you're dealing with function notation like it does when you're just doing arithmetic. Now, for coming up with a graph of the inverse, it is suggested by me and a lot of other people in textbooks that you pull a list of x and y variable coordinates from the graph or the equation, just create a t-table from the equation that's given, and swap the x and y variables or values to make a list of transform points to draw the inverse. And what you'll see is that the relationship between a function and its inverse, which may or may not be a function, is a reflection over the line y equals x. And your book might be explaining the graphical representation between the original function and the inverse slightly differently, but this is a really common one. It's a reflection over the line y equals x, which kind of makes sense because the roles of x and y have swapped. So we're going to graph this function, this y equals a. We have an a coefficient of 1 and a fixed power of 2. It's a fixed power. That's why we call it power functions. Now you might hopefully know what this looks like, but just in case you don't, here's an x and y t-table. Let's pick up some, kind of standard points. Plug each of these into the equation. And actually, so you might like to write the t-table like this, and actually kind of make it almost like a W table. And get your some points. -2, 4, because -2 times -2 is +4. -1 times -1 is 1. I'm just taking each of these values of x and plugging it in for, well, where the variable of x is in the equation, and coming up with some answers. So this is what the graph of y equals x squared looks like, just a parabola. Okay, the best approximation of the graph there. That is the original function. Its inverse is the reflection over the line y equals x. Y equals x is a line whose slope-intercept is 0, y-intercept is 0, and the slope is equal to 1. So we have a y-intercept of 0 and a slope of 1. And with that idea of the roles of the x-coordinate, which of course is our horizontal axis, and our y-coordinate changing, an inverse, instead of, sort of kind of this parabola going up and wrapping around the y-axis, should reflect and go over towards the positive side of the x-axis. Now for that inverse function, we're going to take these values of x and y, swap places, and make a new list of points. Plot them. That was 0, 0, not 0, 1. And that was 4, 2. Don't do your work in a hurry. You'll make silly mistakes. Don't do them on a bunch of cold medicine like I'm trying to do right now. Okay, so there we have our parabola opening up for the original function y equals x squared. And now we have a parabola opening to the right, showing that reflection over the line y equals x. Now, by taking the x and y coordinates and simply swapping places and making a new list of points, I don't have to be an artist to try and see that reflection over the line y equals x. And you can also see, of course, that we have, well, many x values, but we have an x value of 4 giving us two different values, y values of -2 and +2. We have a graph that would effectively fail the vertical line test. So the inverse is not a function. The inverse is just an inverse. Now, if I draw a vertical line through the inverse function, or the inverse, and say I'm doing a vertical line test to test whether it's a function or not, well, of course, the equation of a vertical line is x equals some kind of number. For the inverse, after we took the x and y and changed the places, changed the roles of the independent and dependent variables. So, really in the inverse, what is acting as the variable of x in the original function was acting as a variable of y. So a vertical line test on an inverse is actually a horizontal line test for the original function. So you can look at an original function and determine if its inverse is going to be a function. And I'm kind of giving you a clue of what's coming up. It's a one-to-one test. It's a horizontal and vertical line test. Ooh. And before we move on to the next page of notes, you might like to look at a review of the of domain and range. When you look at the function here, this white parabola, the domain, well, that's about all the x values that are included in the graph, not just the t-table that you made to get some points for representing this equation. Hopefully that didn't mess up the noise there, the sound. But our domain, this white parabola, goes to the left forever and to the right forever. It just keeps opening up. So the domain is going to go from -infinity to +infinity. Or if your book's not using interval notation, you might say that it's just simply all real numbers. And the range, the y values that are included, the lowest y value that's in this white parabola is 0, and then it goes up from there. So with interval notation, that would be from 0 to infinity, or with inequality notation, that would be the range is going to go from y is greater than or equal to 0. Now look at the graph of this sideways opening parabola, or inverse. It does not go left and right forever. The leftmost point in this graph is x equals 0, and then it goes to the right forever. So our domain of our inverse is going to be from 0 to infinity, or x is greater than or equal to 0. See how it used to be the y is greater than or equal to 0, but because the roles of x and y have changed, it's now x is greater than or equal to 0. And the range, well, now this is opening, it's going down slowly, more and more slowly, but it will never quit going down and it'll never quit going up. So it's just going to keep opening up in both directions forever. So all of the y values are included in this graph. Okay, and one last note here. These little like tick marks in the upper right-hand corner, that can be an indication for you and your teacher that you have transformed some original points of x and y. And that doesn't really, it's not really inverse notation. It just means that a transformation has been done. And of course, you might probably only in algebra maybe 2 right now. When you get to calculus, those tick marks are going to mean derivatives, so might be a little bit confusing later. So a written summary of what I said a second ago. The equation of a vertical line is x equals a number. Since the roles of x and y swap to create the inverses, this would now be, in the terms of the original equation, y equals that same particular number for the original function. Determining if a function will have an inverse, the steps here, when you're looking at it graphically, is to do a vertical line test just to make sure that the original thing that's being called a function actually is, and then do the horizontal line test. Now, if that function, if that vertical line and a horizontal line test, no matter where you draw either one of these types of lines in the original function, if each of those, vertical and horizontal, only pass once, then your function is said to be a one-to-one function. Now, that is a vocabulary word or term that I've used in many of my books. This newer Algebra 2 book I'm teaching out of uses a little bit of a different language. It says that it's an invertible function. So a one-to-one function is also another name, an invertible function. So if you pass both the vertical and horizontal line tests, then when you find that inverse, it will be a function. Now, again, just trying to be consistent with the book that I am teaching out of at the moment. I don't really like giving my kids even more stuff to memorize and all these little tiny facts, but it is footnoted that all odd power functions are invertible and all even power functions are not. Now, the key thing here is odd power functions and even power functions, specifically equations that are in that form of y is equal to a times x to the b power, because you start adding more terms to that polynomial and actually create just a general polynomial and maybe just a general quadratic or cubic function or fourth degree polynomial, and you're out of this exact format. Well, then you have to drop this word power, and maybe now you're talking about even and odd functions. Well, not all odd functions are invertible, and not all even functions are, not invertible or not well, actually, even functions will never be one-to-one. But you have some kind of change with the odds. So it's footnoted, well, in the original format of my equation here, because in this format we are looking at power functions. Now I got my notes all messy, but at any rate, I'd rather you just sort of think about the problem, maybe looking at a graph. So determine if the function is invertible. Well, we have y equals 1 x to the fifth, and I don't know why I didn't include some coefficients other than 1 here. So just make it 2. But what does this look like? You could do a t-table. You could type it in your graphing calculator. It is effectively going to look like this. Again, just a power function with an odd degree. In upcoming lessons, we're going to be talking about determining end behavior as well. It looks something like this. And when you look at this graph, you go, well, vertical line crosses once, vertical line crosses once. No matter where I draw a vertical line, it crosses only once. Yeah, that's a function. And when I come through here once, no matter where I draw a horizontal line, it's only going to intersect this graph only once. So it passes both the vertical line test and the horizontal line test, looking for that 1x giving us 1y no matter where we draw a vertical line, 1y giving us 1x no matter where we draw that horizontal line. This is an invertible function because it passes both the vertical and horizontal line test. That's a much better understanding of the knowledge than just saying, well, it's just an odd power function, so it's automatically invertible. That's just a memorization of a fact. When you move on to other functions, it's going to confuse you. So it's in the book. The more I talk about it, I just don't like this kind of shortcut garbage that sometimes textbooks say, well, hey, just remember this, because it doesn't always work. We have y equals negative 2x to the fourth power. You can do a t-table starting with with a center point of 0, a couple of positive x's and negative x's, plug them into the equation, make sure you use those parentheses. But the graph does look something like this. Something to that effect. And while no matter where I draw a vertical line, it's only going to cross once. So yes, this even power function is a function. When I go to draw a horizontal line, we have basically a value of y here giving us two different values of x. So while this is a function, it does not pass a horizontal line test, so it's not one-to-one. It's not an invertible function. And in an upcoming lesson, we will be talking about restricting the domain of these functions that maybe are not one-to-one. Just going, well, how about if we just look at the positive side of the x-axis? That would pass the horizontal line test. So we'll be talking about restricting the domain of functions, so they are going to act in a restricted domain fashion as a one-to-one function. I've got one last example coming up right now. Alrighty, for our last example, we're going to sketch the graph of this inverse function. We have y is equal to negative x cubed plus 2. Do you remember the first page of notes when I gave you the format of a power function? There's a plus 2 here. This equation, I'm saying, I want the graph of the inverse function. I have actually not given us a power function with that plus 2 at the end of this equation. There's a little bit of a transformation there. And there's two terms. Terms are separated by addition and subtraction. There's two terms in this polynomial. It is not actually a power function. So I can't look at that power of 3 and just automatically go, well, it's an odd power function. Therefore, by automatic rules, it's invertible or a one-to-one function. So we're going to do a t-table. We're going to graph it, and we're going to change the role of x and y. And actually, because I haven't done an example yet of actually finding those first two steps about algebraically finding an inverse, we're going to do that as well. So for a t-table here, we're going to pick some values of x, and normally we center our t-table around 0 when there's not much going on in the main power, in the main function of the graph, which is the power of 3, and it's just an x inside that power of 3. That negative is not influenced by that exponent of 3 either. So when there's not much going on inside that parentheses, inside that main function, normally you can be safe with picking a value of x which is 0 and then going a little bit lower, a little bit higher. So negative 1, negative 2, maybe positive 1 and positive 2. We'll add some more points if we need it. We're going to remember that, you can't, two negatives, and they're right next to each other makes a positive. No, you got to do exponents before you do multiplication, and that's what's happening when you see these two negatives side by side and you go, well, those just make a positive. That's multiplication of two negative numbers. You have to do exponents first. So negative 2 cubed, negative 2 times negative 2 is positive 4, times negative 2 is negative 8, and negative 8. Okay, well now we can see that, negative basically 1 times negative 8 is positive 8, plus 2 is 10. And this is going to be negative 1. Now it's positive 1 plus 2 is 3. This is going to be 0 plus 2. Here we have 1 cubed, which is 1, but there's a negative out front. So negative 1 plus 2 is positive 1. And without that transformation of plus 2, the numbers, just a little lower and a little higher than 0 by a unit of 1 would be the same, but with that plus 2, that's not happening. And then we have 2 cubed is 8. Now it's negative 8 plus 2 is negative 6. Plotting these points. And drawing a decent representation of the graph, we have something to this effect. Now, what's the inverse going to look like? Now, as far as just what the inverse is going to look like, we can, as stated before, use a couple of notes indicating that there's been a transformation and swap the role of x and y and make a new t-table and plot those points. Now, by the way, before we plot these points, could you imagine, and I have honor students all the way through pre-calculus and sometimes even calculus, that try and look at a picture very similar to this and draw the inverse, and they inevitably, mess it up because they're just trying to use their artwork, their eye. And probably one of my most common examples of a mistake is this graph that's to the left of the y-axis ends up being above the x-axis. So, take some points out. Negative 210, negative 1, 3, from the graph or from the equation, just simply swap the x and y variables, values, and plot the points. And really, as far as our directions are concerned, that is the graph of the inverse function. You can see that reflection over the line, y equals x, for creating the inverse. This is basically our f of x, and this is our f of negative 1 of x. Now, I just used that exponent format error of negative 1. Well, yeah, look at the original function. It passes the vertical line test. No matter where I put a vertical line, it's only going to cross that graph once, and if I draw a bunch of horizontal lines, we're only going to cross that white graph only once. So that cubic function, not cubic power function because there's a plus 2, does pass the horizontal and vertical line test. So it is one-to-one, it is invertible, and you can see as we have finished graphing our inverse, no matter where we draw a vertical line, which was the horizontal line for the original function, it only crosses once. So our inverse is a function. This is an invertible function. But we didn't actually yet, to finish up this lesson, go through the algebraic steps of finding an inverse and then later determining with this vertical horizontal line test if that inverse is an inverse function. We can take the x and y, change places, resolve for y, so subtract by 2, divide by negative 1, and then the inverse function, what undoes the power of 3, we're talking about inverse functions, what undoes that power of 3, what's the inverse of a cube power? A power of 3 is a cube root. So we're going to apply the cube root to both sides. Because these matching root and power are odd as opposed to even, we can just write y instead of the absolute value of y. And since we've looked at the graph, either the graph of the inverse or did the vertical and horizontal line test of the original function, and we knew or know now that this is an invertible function, we now know that our inverse is a function, so I can use this extra little nice notation of why the inverse function is y is equal to the cube root of 2 minus x. That is the end of my last example. I'm Mr. True. But wait, there's more. Vocabulary, one more vocabulary in this section. End behavior. And it's end behavior specific to power functions, but actually it's end behavior for all polynomials where you have one independent variable and all the exponents are positive integers. If you have a polynomial with an even power, the highest degree, or you only have one exponent when we're talking about power functions like exponent of 2 or 4 with a positive leading coefficient, a positive a, here we have positive 1 and positive, try negative 2 and negative 1 as we have down here, but with a positive leading coefficient, your graph is going to go up to the left and up to the right. Or in limit notation, the limit as x approaches negative infinity for your function, f of x, is going to go to positive infinity. So as x decreases, eventually the function is going to start shooting up and go to positive infinity. And end behavior is not about what's in the middle of the graph or often near the origin. It's as x is approaching extreme values of negative and positive infinity. Now, power functions don't have a lot of bends. They don't have a lot of bends in them. They generally just have like one or maybe two if you consider that odd degree, like a cubic function. But as you add terms to these power functions and you create polynomials, there can be a lot of bends in the middle. But the end behavior, up to the left, up to the right. If you have a negative leading coefficient, like here we have negative 2 or negative 1, then limit as x approaches negative infinity, the graph is moving to the left, your y value is going to become ever more and more negative. It approaches negative infinity. And as you have x values approach positive infinity, the graph is once again going to go down to negative infinity. So even power polynomials, the end behavior to the left and the right is always the same. With odd powers, and I'm saying this in general because it's not, again, just to odd power functions. If you have a positive leading coefficient, like here y equals 2 times x cubed and y equals x to the 7th, your end behavior, unlike with your even power functions or polynomials, is not the same, it's the opposite. And a standard positive leading coefficient, as x approaches negative infinity, you're moving to the left on the graph, the y values are going to approach negative infinity. It's going to go down forever. So it's, as you go to the left, it's down forever. As you go to the right, it's up forever. The limit as x approaches infinity of f of x, that limit is going to be positive infinity. And when you have a negative leading coefficient, remember transformations, a negative leading coefficient on a function just reflects the graph over the x-axis. Well, then your behavior is opposite. So instead of going down to the left, it goes up to the left and down to the right instead of up to the right, like you had with a positive leading coefficient. Now I'm done. I'm Mr. True. Bam! Go do your homework.